conservation of mass. All right, since we're talking about chemical reactions and everything going on with that, well, one highly, highly important principle to understand when we're talking about these chemical reactions is, well, this one simple principle, right? And the simple thing is that matter cannot be created or destroyed. So for all the different kinds of chemical reactions we're going to be talking about this chapter, just think those atoms, right? They're not created or destroyed. The matter that's in them can't be destroyed, or new stuff can't be created. Now you can change it around and mix them all around and everything. And in some cases during chemical reactions, it might appear like, oh my gosh, something has vanished in the thin air, but the atoms are always still there. And in fact, even if you went to the extreme of like, okay, you could split an atom now, it really hasn't destroyed the matter. You've got little bits and pieces of protons over here and little bits and pieces of the protons over there kind of thing. So you can't create or destroy matter, right? So we're going to learn later this chapter about the 4 different types of chemical stories, or the 4 different most common types of chemical reactions for it. So we'll learn about all that. But in every case, right, think about it kind of like a scale right here. Whatever you have at the beginning of the story, let's say if like this was 1 atom of titanium and this was 1 atom of aluminum, right? They might mix together, but you still have that same 1 atom of one and 1 atom of the other one, right? So some titanium and some aluminum. So even though they might mix around and things look different in a chemical reaction, they're all still there. They have to be accounted for in order for it to be a true statement for it. So for conservation of mass, basically you cannot create or destroy any matter in a chemical reaction, right? Everything that's there before is there after kind of thing. So for an example, think of any chemical reaction you want to, whether it's like an explosion, banana rotting, fire. There were a whole bunch of them that we talked about, earlier and everything like that. The non-example could be like a disintegration, right? Have you ever watched a show and they're like, beep, 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 with some kind of gun, and a person just vanishes right before your very eyes kind of thing? That is not true. That's bad science fiction right there, right? That's not the way it works at all. Oh, here you go. Here's my example, right? Here we go. They try to shoot something, they get shot, and they just, goodbye, right? That is not good science fiction at all, because we know matter's not just simply destroyed. A better example could be, well, this guy right here, right? Ever see a movie where someone's disintegrated or destroyed, and instead of just vanishing in the thin air, they actually, they kind of like crumble apart, right? Their mass is going somewhere else. It's just kind of blowing away. That, scientifically speaking, is very possible, right? So you've got, a possible disintegration kind of thing going on versus the impossible for it, right? So, here we go. So since we're talking about disintegration and everything like that, let's kind of lighten the mood a little bit. Chemistry joke of the day. Right, here we go. What did the angry electron say when it was repelled? Okay, one electron's not very happy. It says, let me atom. Oh, come on. Sometimes they're so good you got to laugh a little bit. All right. Let's see here. So for conservation of mass, let me show you this short little video describing what's going on here.
Where does all this stuff come from? This rock, that cow, your heart. Not the things themselves, mind you, but what they're made of. The atoms that are the fabric of all things. To answer that question, we look to the law of conservation of mass. This law says, take an isolated system, defined by a boundary that matter and energy cannot cross. Inside this system, mass, aka matter and energy, can neither be created nor destroyed. The universe, to the best of our knowledge, is an isolated system. But before we get to that, let's look at a much smaller and simpler one. Here we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. With a little energy, our molecules can really get moving. These atoms can bond together to form familiar molecules. Here's water, and here's carbon dioxide. We can't create or destroy mass. We're stuck with what we've got. So what can we do? They have a mind of their own. Let's see, they've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar and some oxygen gas. Our atoms are all accounted for, 6 carbon, 12 hydrogen, and 18 oxygen. The energy we applied is now stored in the bonds between atoms. We can re-release that energy by breaking that sugar back into water and carbon dioxide, and still, same atoms, Let's put a few of our atoms aside and try something a little more explosive. This here is methane, most commonly associated with cow flatulence, but also used for rocket fuel. If we add some oxygen and a little bit of energy, like you might get from a lit match, it combusts into carbon dioxide, water, and even more energy. Notice, our methane started with 4 hydrogen, and at the end, we still have 4 hydrogen, captured in 2 water molecules. For a grand finale, here's propane, another combustible gas. We add oxygen, light it up, and boom, more water and carbon dioxide. This time we get 3 CO2s, because the propane molecule started with 3 carbon atoms, and they have nowhere else to go. There are many other reactions we can model with this small set of atoms, and the law of conservation of mass always holds true. Whatever matter and energy go into a chemical reaction are present and accounted for when it's complete. So if mass can't be created or destroyed, where did these atoms come from in the first place? Let's turn back the clock and see. Further, too far. Okay, there it is. The Big Bang. Our hydrogen formed from a high-energy soup of particles in the 3 minutes that followed the birth of our universe. Eventually, clusters of atoms accumulated and formed stars. Within these stars, nuclear reactions fused light elements such as hydrogen and helium to form heavier elements such as carbon and oxygen. At first glance, these reactions may look like they're breaking the law because they release an astounding amount of energy seemingly out of nowhere. However, thanks to Einstein's famous equation, we know that energy is equivalent to mass. It turns out that the total mass of the starting atoms is very slightly more than the mass of the products, and that loss of mass perfectly corresponds to the gain in energy, which radiates out from the star as light, heat, and energetic particles. Eventually, this star went supernova and scattered its elements across space. Long story short, they found each other and atoms from other supernovas, formed the Earth, and 4.6 billion years later got scooped up to play their parts in our little isolated system. But they're not nearly as interesting as the atoms that came together to form you, or that cow, or this rock. And that is why, as Carl Sagan famously told us, we are all made of star stuff.
All right, so there you go. Another example for conservation of mass right there. How about this one? If you need a simpler one, right? How about this, right? Let's say good news happens to you, right? All of a sudden, someone calls you up and says, you just won a brand new Ferrari. And after you're done dancing and jumping around like, yay, I won your Ferrari and everything like that. Well, you get home, you jump in the car, you drive out of the driveway and everything like that, and all of a sudden, oh my goodness, that happens because you don't have a driver's license yet. What were you thinking? Oh my goodness. But anyway, here's the example, right? Is this conservation of mass, right? Definitely a change has happened right here and everything like that. So we would definitely say, okay, there was a physical change that happened to your literal brand new Ferrari and everything like that, right? But is it conservation of mass, right? Is everything still here that was there before? Well, sure. You know what I mean? Like if you were to get out of scale, right? You got a big scale going here and everything like that. You put the car in the scale first, the way it was, right? Recorded how heavy it was and everything. Then you found the mass of the car after the accident. It's going to be exactly the same. Now, you'd have to be very careful, right? You'd have to make sure, okay, we swept up every little tiny piece of glass or plastic or rubber or whatever it is that might have fallen out or anything like that. But it would be exactly the same, right? For it. And I mean, that's going to be a really expensive car bill. I don't even know how much it would cost to fix a Ferrari like that and everything, right? But then it gets even worse. The car explodes, right? And then your car that used to look like this now looks like this. Oh my goodness. It's even worse now, right? But would that still be conservation of mass, right? I mean, definitely now there was a physical reaction and now you've got a chemical reaction that happened too, right? But is it still the same thing? And the answer is yes. It turns out it's still going to be the same thing. Now you'd have to be careful. You'd have to rewind a little bit. You'd have to be careful to capture like every little tiny piece of the car that flew off of it, you'd have to capture. You'd have to capture every little bit of smoke and ash and the gases that came off of it and everything like that. But if you did that and you actually measured how much everything was, right, that's still here, everything that came off the car, it would be exactly the same, right? So it's not creating or destroying anything new as far as the atoms go. It's just destroying your really nice car. All right, so while the first one might be fixable, this one's not. I mean, this one's a total loss right there. It's too bad, so sad. Normally in class, right, what I do is we talk about this where I'd have a triple B balance right here. We put some candles on it, light the candles up, and then watch and see what happens, right? Slowly over time, there's a chemical reaction going on right here, right, where you have the wax. Well, basically, you've got the wax being burnt up and the wick being burnt up and everything like that, right? That chemical reaction or the fire part of it, some of the particles are floating up into the air. So what happens is we can watch really carefully, and it doesn't take long at all. And you can see that the changes, right? The mass changes on it. There's less mass here. And I mean, the answer, where's all that mass going? Since nothing's created or destroyed, it's floating around in the room, right? That's what's happening. So anytime, you have a fire burning or candles going and everything like that, that's what, dust is essentially around a house, right? It's just dirt and everything like that. It's the burnt up ashes of the candle, right? It floated around the room and landed on your chair, on the floor, on the desk or counter or something like that, right? So that would be an example of what we call an open system, right? So for these chemical reactions, there's two ways you can kind of classify them. The first one is an open system, kind of like the candles burning over here. The smoke and ash and gases, they're able to freely transfer around all over into the room that we're in and everything, right? So matter is allowed to come and leave if it's called an open system, right? For my example, I always like to use just a candle burning openly in a room, or how about an ocean example, right? In an ocean, let's say a big coral reef, fish are allowed to swim into the reef, swim out of the reef, and everything like that. They're like, if there's a fish just kind of swimming along, and it's like, oh, look, that reef looks pretty. It can come on over here and just kind of hang out and find whatever it needs to find to eat or anything like that. If all of a sudden a big shark moves into the reef, all the fish can be like, oh, swim away, and go somewhere else and find a different reef to go live in and everything, right? That's an example, again, of an open system going on there. Now, the opposite of this would be a closed system. Right, a closed system is where things cannot come and go, right? So in the water fish example, well, yeah, this guy right here, right? This would be a closed system. This fish can't get out of this. It's stuck in this tiny little jar right here and everything. It seems really cruel and mean and everything like that, right? As opposed to the other fish, right, swimming around in their reef. They could come and go as much as they want. This fish can't, it's just kind of stuck there, right? Or the other example, if you want to do, another example, instead of, you could do this either with a candle or just with some paper and everything like that. If you have a candle burning and you put like a big glass jar over top of it, right, then what happens is there's only so much oxygen inside of this, and the candle burns out really quickly. Or in this case, a piece of paper would burn out super, super quickly. In fact, it's actually kind of scary how fast it goes out because, this jar right here, let's say it's almost the size of like a 2-liter soda bottle kind of thing. And if you have a candle burning and you put this over it, within like 2 seconds, maybe not even that, the fire, it uses up all the oxygen that's inside this container and burns out. It's kind of scary how much oxygen and how quickly it burns out when you do, that kind of short little mini experiment right there. All right, let's see another example of this conservation of mass in action.
Into the small container, some heavy whipping cream is being poured. Heavy whipping cream, which is also called heavy cream, has a milk fat content between about 36 and 40%. Cream also has proteins, and one of the important proteins is a protein called casein. With a high amount of fats and proteins, you can see the liquid is very thick. Here we have some vinegar, also known as acetic acid, and it's a clear liquid. Onto the balance will be the two chemicals that we looked at before, including an empty dish, and we're going to measure the mass of the two chemicals, also known as the reactants. Here's our empty dish, and we're going to put the vinegar first into the empty dish, And then what we're going to do is follow that with the cream. Now, as you can see, as the cream's being poured into the vinegar, it's not spreading out all the way. You can see it's kind of congealing, or it's becoming thicker. And is a chemical reaction happening or not? Well, one of the signs we can see it, that a chemical reaction has happened is that when two liquids react to form a solid, that's a chemical reaction. That's called a precipitate. And that white stuff is a precipitate. This now leads to our question. What will the mass of the reactants compare to the mass of the products? Let's put the products onto the balance and our empty dishes that contain the reactants before. Now the reactants mass was 61.4, and let's see what the mass of the products are. Looks like it's 61.5, and now it's 61.4. So it looks like they're the same. So this demonstration shows that the mass of the reactants equals the mass of product, and that no matter is lost during a chemical reaction.
All right, so there you go.
Was the acidity of the vinegar caused the casein protein to tangle into solid masses called curds. This is essentially how cheese is made. And so that's how you get a solid product from that liquid milk. So this is in fact a chemical reaction. And it's a chemical reaction where, yes, the mass of reactants equals the mass of the products.
There you go. So think about any of the products that you like to eat that basically are spoiled milk. Just think about it. Cheese, yogurt, things like that. I mean, all they really are just, milk that's gone bad, really, right? So all of that, it requires a chemical reaction. And I like this video because it zooms in really, really close for you so you can really see like what's happening with it and everything. But they had all the stuff before the chemical reaction happened, including the dishes and little cups and everything like that. And then after, even though there's a chemical change and there was no solid substance before the chemical reaction, but now there is a solid substance, well, it had exactly the same mass, right? And that's kind of the key of this whole lesson for today is matter is not created or destroyed in a chemical reaction, right? It's always still there. It just kind of rearranges itself and everything. So even though with your eyes, it might appear like something new has been created that wasn't there before, and it seems like matter is being either created or destroyed before your very eyes, it's not. It's just being rearranged and creating some new substance from, the ones that were there before. It's being, reconnected and everything like that. Think about it like Legos. You build some totally different creations with it and everything, but it's still the same little pieces of Legos that were there before, for our example of conservation of mass. All right. Remember to take the quiz when you're finished watching this video so you get all the points for it.